Hi, class. Welcome back. Today we'll be discussing Chapter 11, Endpoint Security. We're going to quickly highlight the related domain objectives from CompTIA or CompTIA. I'm not going to go through or read through every single one, but I'm just going to put them on the screen in case you want to see them for further reading and further research. There's one more page coming up after this. And again, the main context for what we're looking at here is the regarding endpoint security. So the main focus is, like, for example, domain security operations in the context of endpoint security. The operating systems that we're working with themselves can contain vulnerabilities. Windows, Linux, Mac, any of these operating systems or any other operating systems out there can contain vulnerabilities. Patching is essential as it is the primary way that we address issues with our operating systems or vulnerabilities with our operating systems. We've also covered this before, but default settings, default configurations can be another major vulnerability that we can encounter. Default administrator usernames, default administrator passwords. We can have other issues regarding configurations or other vulnerabilities related to configurations. Unlike default, these are configurations that were made by an administrator or a user that are just less secure. They don't follow best practices. Another vulnerability we can encounter is misconfiguration. This is a situation that arises due to human error, some mistake in the configuration process. Ideally, we have good processes in place that help to prevent or mitigate the risks associated with misconfiguration. Firmware. Firmware is embedded software, essential for device operation, closely integrated with the hardware. While firmware in computers and mobile devices can often be updated, updates may require manual intervention and are not always automated. Firmware has vulnerabilities. Firmware is susceptible to attacks through various means, such as executable updates, downloads of malicious firmware, or remote updates. Firmware updates can be especially severe. They tend to persist through operating system reboots and updates. Firmware vulnerabilities can be especially severe. They can persist through reboots, they can persist through reinstallation. An example of this would be malware like Moonbounce targeting SPI flash memory. The Moonbounce malware embedded itself in a BIOS chip and survives through drive formats. One security measure we can take is firmware validation. We can use a handful of advanced security controls such as trusted boot to protect against firmware manipulation. This next section of the slide is a little off topic, but it's definitely an important concept too. We want to talk about life cycle of product or life cycle of hardware. Up first, we have end of sale. This is the specific date in which the vendor will stop selling the product. We have end of life. This is the period after the product is no longer sold but still remains supported. We have end of support. This is the specific date when the vendor will stop providing support for that specific software, hardware, or whatever the product may be. Legacy hardware. This is anything that is out there, product, hardware, software, whatever it may be, that is past the point where it is no longer supported. So it is unsupported hardware or software or any kind of product out there in the IT environment. Since one of the key focuses of this chapter is going to be protecting endpoints, I just wanted to take a quick second to clearly define what an endpoint is. When we're talking about an endpoint, we're usually talking about the end devices in our system or in our network. Could be servers, could be desktops, could be mobile devices. That type of thing is usually called an endpoint. And so in the context of this chapter, we're primarily talking about how do we secure these endpoint devices. One crucial aspect of securing our endpoint devices is called boot integrity. Boot integrity. When our system starts, how do we make sure it starts securely using the correct operating system and correct boot processes? There's two key methods that we're going to focus on, which is secure boot and measured boot. Again, that is secure boot and measured boot. Secure boot utilizes a signature database to verify that only software and firmware trusted by the OEM are used during the boot process. Measured boot measures and logs each component of the boot process, from firmware to boot start drivers, without initially validating against a known good signature list. It uses the UEFI firmware to hash boot components storing data in Trusted Platform Module, TPM, for remote validation and attestation. I just want to make a note of some key terms and key concepts. We're going to burn through these four really quick. TPM enhances system security through hardware-based functions like remote attestation, binding, and sealing of data. HSM, Hardware Security Module, dedicated hardware used to generate, store, and manage encryption keys securely. Key Management Service, KMS, a service that helps manage cryptographic keys for organizations securely. This provides a centralized mechanism for creating, distributing, and controlling encryption keys. Last on the list, Secure Enclaves, specialized hardware used to protect the lifecycle of cryptographic keys and maintain security, even if the main CPU is compromised. In the context of endpoint security, we have a handful of tools or resources or concepts that we can manage. Antivirus and anti-malware tools, allow and deny lists, EDR and XDR, data loss prevention, and network defenses. We're going to go over some of these individually here in a second. Antivirus and anti-malware software form a crucial defensive layer in enterprise environments, helping to mitigate threats despite evolving malware techniques. Sometimes they are considered the last line of defense, often considered the final safeguard against system infection and compromise. These are four very common detection methods that we use. Signature-based detection, heuristic or behavioral-based detection, AI and machine learning, and sandboxing. Signature-based detection identifies malware based on known patterns or hashes. Heuristic or behavior-based detection analyzes the action of the software to detect new or unknown types of malware. So we're looking at the behavior of the malware or virus and trying to decide or recognize that it's malware or virus based on that behavior. AI and ML, machine learning techniques, utilize extensive data to enhance detection capabilities, incorporating elements of both heuristic and signature methods. Sandboxing. In a sandbox environment, we have a controlled environment where we can run and analyze suspected or confirmed malicious code safely. Up next, we have allow lists and deny lists. Sometimes these are referred to as whitelisting or blacklisting. Or an allow list, or sometimes called a whitelist. These tools enable administrators to create a list of approved software, applications, or systems, sites, whatever that may be. Anything not on the list is typically blocked or removed, so we have to give explicit access to things that we want to be able to use. Conversely, a deny list or a blacklist, in this form of list, we are blocking things explicitly. Everything else will be allowed. There's some pros and cons to each option. Allow lists will generally provide a higher level of security. You're only explicitly allowing things that you know are safe, or at least should be. Deny lists, however, offer a little bit more flexibility and can often be a little bit easier to manage and use. Up next, we're going to talk about EDR. This is an endpoint detection and response tool. These enhance security beyond traditional anti-malware tools. One of the big points is they are capable of monitoring, collecting, analyzing, and responding to data or events that may happen. Up next, let's look at XDR. This is essentially an extension of EDR, or an extended version of EDR, Extended Detection Response, XDR. We're extending the scope of EDR by incorporating data from the entire technology stack. So we're including endpoints, cloud services, email, and other platforms. So the breadth of technology in the stack that is covered, that is the main difference between EDR and XDR. Data loss prevention, DLP. Again, these are tools that are designed to prevent both the intentional and accidental theft or loss exposure of sensitive data within an organization. So as the name implies, data loss prevention tools are tools designed to prevent the loss of data, intentional or accidental. Before we deploy data loss prevention tools, it's very important to have some sort of scheme in place, some data classification scheme in place. So the first step would be to implement the use of data classification schemes. We're going to talk about network or host-based defenses. A lot of these things correspond directly to other concepts we've talked about in networking. We've talked about network-based intrusion prevention systems. We've talked about network-based intrusion detection systems. We've talked about network-based firewalls. We have the same kind of concept for most of our endpoints or for our standard computers out there. We have firewalls, we have host-based intrusion prevention systems, and we have host-based intrusion detection systems. Again, the primary difference between these and the network-based systems are these are designed for endpoints, for our host devices. So the key role of our host-based firewall will be much similar to, or will be very similar to a network-based firewall, except for it will be blocking and allowing traffic and application services, ports, etc., for a single host or endpoint on our system. A host-based intrusion prevention system will behave much like a network-based intrusion prevention system, except for it will serve a single endpoint on our system or a single end device on our system. Again, a quick recap on that is it will analyze and take action on traffic before it is processed by the applications or services. We also have a host-based intrusion detection system. Again, this is similar to a host-based intrusion prevention system, except for it lacks the ability to block the traffic. So this one, the HIDs will simply detect the issue, or as a HIPS will actively will take action to prevent or block or disrupt what it sees as a threat. This is kind of a quick layout of a simple network where we can see kind of why these host-based devices or host-based systems are important. Under this kind of simple network model, we have internet traffic that comes through the firewall, a network-based intrusion prevention system that will filter traffic, and then we could see that potentially, depending on how our network is set to work, all this traffic that is passed back and forth between these individual devices is not necessarily going to be sent back out the network through the firewall, through the intrusion prevention system. So it's important for these end devices to have their own level of security. And in this diagram, we have one that just has a host-based firewall and a quick description of what that firewall is doing. We have one that is a host-based intrusion prevention system and a quick description of what that is doing. And again, they're not mutually exclusive. The smart device here on the end has both of those features active. These are some key concepts that the Security Plus exam explicitly highlights. Encryption, installing endpoint protection, host-based firewalls, host-based intrusion prevention systems, disabling ports and protocols, changing default passwords, removing unnecessary software. We covered some of this. We're going to cover some more of these aspects as we move through this class. Let's talk about service hardening a little bit. Our objective here is to reduce system attack surface by minimizing open ports and active services. One of the key methods for solving this is we disable unnecessary ports and protocols and prevent remote exploits. The general guideline that we follow would be that only essential services should be open and only things that are necessary for our network or system to work. Some tools that we can use: port scanners. This will help us identify open ports. Implementation. This is something that we don't necessarily need to do just once. This should be something that we regularly audit and adjust based on our system's needs. In addition to the ports here, while it may seem like a brute force memorization type thing, when we're auditing logs and reviewing the status of our network, we probably want to remember or just know from our Network Plus class that we took previously which ports are unsecure or which protocols are unsecure. So if we saw traffic on port 21, port 23, or port 80, we'd probably know that's unsecure or unencrypted traffic. In addition to blocking services with firewall rules, we can also block or disable services in Windows directly. In the screenshot here, we have services.msc open, and we're going through the services there. And in this case, it looks like we're about to disable the remote desktop service. For other operating systems, you generally have the ability to disable or enable services as well, though the process may be a little bit different. A little more on network hardening. One of the Best ways we can harden our network is to use VLANs. We can employ VLANs to segment networks based on trust levels, user groups, or system types. That process will enhance security. Another thing we can do is create guest networks or separate networks for less secure devices like IoT devices. We've covered this a few times throughout this semester, but again, a key thing, we want to change default passwords. Another hardening practice, remove unnecessary software. There are several benefits to removing unnecessary software. One of the primary reasons to remove unnecessary software during the hardening process is to reduce our attack footprint. We also lower the burden of patching, reduce required system monitoring. Sometimes this in the real world can be tricky to implement. You may work with several other departments or several other organizations, and you may not know as an IT professional exactly which applications every single end user or every single department interacts with every day. So you generally want to perform audits and identify and uninstall software that you don't need. Generally, you want to uninstall pre-installed software or bloatware that may come on a specific device or come pre-configured on a specific device. Another thing we may want to do is harden the registry. Again, one of the key roles for the registry is to track system configurations and operations. Attackers can target the registry to launch programs, access data, conduct malicious activities. Key strategies we can use to harden the registry: configure permissions, disallow remote access, restrict tool access. As a system administrator or a security administrator, something you may deal with a lot is group policy. Essentially, group policy allows centralized management of Windows settings through group policy objects. These can impact various system configurations, such as user account policies, security settings, software installation rules, etc. Auditing an organization's policies can be very tricky. Sometimes one of the best approaches can be just to use a policy analyzer to help you evaluate the state of the organization or the GPOs that they have in place. Configurations, standards, schemas, and system hardening. Tools for configuration management. For Mac OS, Jamf Pro would be a common tool. This is a third-party tool that manages and enforces security standards. For Windows, you could use something like Configuration Manager. There are also open source options like CF Engine. An important part of configuration and standards is setting baseline configurations. We want to establish baselines. We can have several different baselines for different users or different systems, but it's definitely an important part of this process. We also want to ensure that we have some kind of configuration enforcement. If we're managing hundreds or thousands of devices, this is absolutely crucial. We need to ensure that there is some compliance with our established baselines. The security baseline lifecycle generally has roughly 3 phases. 1, we want to establish our baseline. 2, we want to deploy that baseline. And 3, we have to maintain the baseline. Patching and patch management are critical for security. Oftentimes, the vendor or the organization that you're working with has done most of the work for securing their applications, software, hardware, whatever it may be. As an endpoint manager for security, it's your main responsibility to deploy those fixes, to deploy those security updates. We have a handful of tools that we can take advantage of. One is automatic updates. Many software applications or packages will have the option to automatically deploy updates. That's one method we can use to ensure that our applications stay up to date. Enterprise systems. We can use tools like Microsoft Configuration Manager or other third-party tools that we can use to manage application patches and updates. For mobile devices, we may want some kind of MDM, Mobile Device Management, MDM. We can do things like manage software versions, apply patches, control security settings on our mobile devices for our organization. Encryption. The main purpose here is to protect data on disks from unauthorized access. We covered a little bit of this last week. Full disk encryption. This encrypts the entire disk. Volume encryption targets specific disk volumes. File and folder encryption secures individual files and folders. We're going to talk a little bit about embedded systems. I'm going to give you the textbook kind of definition up here. Definition: embedded systems are specialized computer systems integrated into devices across various industries, including industrial machinery, vehicles, and medical equipment. Embedded systems use operating systems. Many use real-time operating systems, RTOS, real-time operating systems, for immediate data processing needs, while others might run familiar systems like Linux. A little bit more on embedded systems. Let's look at first some of our security considerations. Connectivity. We need to assess how embedded systems interface with the world. Vulnerabilities. We need to identify network services, assess default configurations, and determine security weaknesses. Patching and updates. We need to learn how the system is updated, establish a regular patching cycle, and ensure updates match the device's usage and threat model. Risk management. Documentation. We need to acquire detailed documentation on the system's operation and security measures. Incident response. We need to plan and document responses. Security practices. Include robust security practices in our acquisition processes and operational procedures. Security implementation. Network segmentation. Again, like in most cases, we want to use segmentation to protect vulnerable devices. Baseline security standards. We want to apply and maintain security standards for all embedded systems. SCADA and ICS. ICS stands for Industrial Control System. ICS, Industrial Control System. It's a broad term for systems used in industrial automation. SCADA, Supervisory Control and Data Acquisition. Specialized architecture used in complex industrial processes and infrastructure management such as power and water distribution. A couple key terms that we may want to look up for. RTUs, Remote Telemetry Units, RTUs. These collect data from sensors. RTU. Up next, PLCs, Programmable Logic Controllers. These control and gather data from industrial devices like machineries. Securing Internet of Things. These devices generally have poor security practices, short support lifespans, and the vendors may not have the best practices for how they handle our data or how they collect our data. These are some constraints that we may encounter with embedded systems. Limited computational resources. Embedded systems typically have less processing power, memory, and storage than PCs. Connectivity limitations. Many embedded systems lack network connectivity or cannot use it effectively. Cost and replacement issues. While some embedded systems are relatively inexpensive, others might be extraordinarily expensive or difficult to replace. In these situations, we may have to implement some kind of compensating control. Okay, that's all I have for you. I hope you all have a wonderful week. Bye.